Welcome back. We are going to start with our analysis of noise and look into the noise minimization of our differential stage that we discussed in the last example. So, before we arrive at the noise analysis, we will just have a brief recap of the concepts associated with noise, the time domain representation of noise, frequency domain representation of noise, and then finally transistor noise models, and then looking at the circuit analysis based on those models. Let us get started. So, noise can be seen as a random signal which is having a close to 0 mean and a distribution of amplitude which can be relatively Gaussian. So, you can have a Gaussian white noise which is having an amplitude distribution given by a Gaussian characteristics. That means, the probability of the noise amplitude close to the 0 point will be maximum, and as you go away from the 0 point it will be reducing, approaching 0. So, this is the amplitude distribution. So, basically here I am plotting the statistics of the amplitude. So, on the x axis I have V n, magnitude of V n plotted, or you can say V n plotted on both sides of zeros, and on the y you have the statistics, that what is the probability of the noise amplitude lying in a certain domain. And on an average, as we can see, according to this distribution, the mean will be 0. So, if you add up the noise samples for a sufficiently long duration, the mean will turn out to be 0. And if we look at the frequency spectrum, so this is the time domain representation. So, I am talking about the amplitude, how it is distributed in amplitude domain as we look at the samples. Likewise, if you look at the frequency domain representation, this is V n as a function of time. Frequency domain representation would determine the spectrum of this noise, how it is spread in the frequency domain. So, there are two major frequency spectrum of the noise that we encounter in our active and passive devices. One of them is white noise. That means, the noise component is uniformly distributed across the entire frequency range of interest. That means, whether we take low frequency f1 or a significantly higher frequency f2, the noise component or effective energy contribution of the noise will be similar at both these frequencies. And the another dominant or bothersome noise component that we have in our circuit, which comes from MOSFETs, is 1 upon f noise, where the noise spectrum increases with frequency. So, if I am plotting the magnitude of noise or magnitude of energy in a certain frequency packet of the noise, it will go on increasing with a certain frequency, and that is termed as 1 upon f noise. So, we will be looking at both these representation, time domain and frequency domain representation of noise, and the concept of noise spectral density, and then look at the MOSFET models. So, if you look at the concept of noise spectral density, it basically gives us the energy component of noise in a certain bandwidth delta f or delta omega. And to do that, basically we need to visualize a noise source V n t. You can call it, you can denote it by a star mark, because it is not having any fixed polarity. It is a random noise signal. So, noise voltage can be generated represented by a voltage source with star marked, and I can call it V n t. And I have a band pass filter over here, a very narrow band pass filter, assuming that you are having a band pass of 1 hertz bandwidth, and after that you have a resistor load of 1 ohm, and whatever V n t you apply, it is passed through this filter for with a certain frequency f naught, and you are analyzing the voltage achieved at this particular point, and you are taking the mean square of this voltage. So, you are taking output V o n square over time. What is the significance of mean square? So, if we want to obtain the power delivered by this noise source to this 1 ohm resistor, I need to look at the mean square value. So, for a large time duration, if I just find out V o n t square and V o n t square divided by R, which is 1 ohm, that gives me the power delivered instantaneously at a particular time instance, and the dt of that for a particular time divided by that time duration will give me the average power delivered during that time t. So, that is why we can look at the mean square value VON square delivered to this 1 ohm resistance, and we can quantify the power delivered by that noise source, or in other words the energy content of that noise source in a certain frequency range, in a certain 1 hertz frequency range across a center frequency f naught. So, now if I keep on sweeping this frequency from very low values going all the way to high frequencies. So, at each frequency value I will get certain magnitude of VON square, which basically tells us that what is the energy content of this noise signal VON t at that particular frequency. And finally, I join all these curves to obtain the Vn square per hertz, which is the power spectral density of the noise, or simply noise spectral density that we obtain from that source. So, this is basically telling us that at a particular frequency f naught, if I am taking a 1 hertz bandwidth, within that what is the energy content of that noise signal, or if I connect it to a 1 ohm load, what will be the power delivered to that 1 ohm load because of this noise signal. So, this is the general frequency domain representation of noise. It can also be represented in terms of Vn per root hertz. So, I can take a square root and I can represent this unit as a Vn per root hertz, and in that case we have the overall noise shape. The spectral shape remains almost same, only thing is the magnitude becomes square root. Now, if we look at the bandwidth definition over here, I have chosen it to be 1 hertz, and definitely that would mean that you are having the power delivered in this 1 hertz bandwidth, and then you are denoting it as the energy or power delivered per unit hertz. But definitely this definition also has to be valid at much lower frequencies as well, much lower than 1 hertz. So, if you have to get the spectral density at frequencies f lower than 1 hertz, then only thing that you have to envision is that the bandwidth of this filter that you are having is reduced, it is much lower than that particular frequency. So, if you are going say for a 0.1 hertz frequency and you want to get the spectral density value at 0.1 hertz, then of course, in order to get the frequencies at 0.1 hertz, at 0.11 hertz and 0.12 hertz, you will need to use a bandwidth which is further smaller, much smaller than 0.1 hertz. So, probably I will use a 0.01 hertz bandwidth ideally, just conceptually. So, for obtaining the spectral density for frequencies lower than 1 hertz, what you need to see is that this conceptual filter will be having a bandwidth much lower, 0.01 hertz, and then I will keep shifting it in small steps, say 0.01 hertz, and within that I will get the power delivered and divide that power delivered by that bandwidth delta B of 0.01 hertz to get the power delivered per unit hertz, or Vn square per hertz. So, that is how I can take care of lower frequencies. So, this is how conceptually we can arrive at the noise spectral density of the particular noise source. Now, the other issue is time domain representation. So, if you are having two independent noise sources, say Vn1t, and you are having another one, say Vn2t, and then you are putting a resistor over here, Vn1t and Vn2t. So, suppose you are having two independent noise sources and you are looking at the final value coming over here at this load resistance, maybe 1 ohm. In that case, if I look at the time domain value, I will simply write Vo n t is equal to Vn1t plus Vn2t. And once again, in order to find out the power delivered by this noise source, the combination of these noise sources, I will take the mean square value, and therefore, I will write mean square value as Vn1t square plus Vn2t square plus 2 times Vn1t times Vn2t, and then integrate this over a sufficiently long duration. Integrate it over a sufficiently long duration dt over t and divide the whole thing by t. So, this is what I will do for obtaining the mean square value for the combined sources, and this can be seen as the mean square value of Vn1t, because if I just take this integral and take only the first term Vn1 square t dt, Vn1 square t dt integrated over 0 to t divided by 1 upon t, that is nothing else but mean square value of the first noise source. So, I can call it Vn1 square with a bar to represent the mean square value. Likewise, I can look at the Vn2t. So, this second term Vn2t square dt integrated over 0 to t divided by 1 upon t once again gives me the mean square value of Vn2. So, I can call it Vn2 square, and we have the remaining term as 1 upon t 0 to t to Vn1t Vn2t dt. Now, this term is something like a correlation between the two random noise sources Vn1t and Vn2t, and if the noise sources are independent, they are coming from independent sources, independent transistors or different resistors, they are going to be uncorrelated, and therefore, this term may altogether vanish. Therefore, when we want to get the overall noise power because of the two independent sources coming together, I need to add their mean square values. So, I can obtain the mean square noise spectral density of the first source, mean square noise spectral density of the second source, and those mean square values need to be added to get the overall effect. We cannot add the time domain value, we do not add the Vn1t and Vn2t, rather we add the Vn1 square, the mean square value of the first source plus the mean square value of the second source. So, basically this is going to give me the overall power delivered by the effect or by the combined noise sources Vn1t and Vn2t. Just to visualize how these noise sources will be uncorrelated and getting cancelled. So, if these two are the simplest cases, you are having only two levels in the noise, equal probability each noise source can apply take 1 or -1 values. Likewise, the other source can also take by equal probability 1 or -1 value at different time instances. So, this is your Vn1t and this is your Vn2t. So, for a sufficiently long duration, each sample I am assuming that it can take only two values, either it can go -1 or +1. Assuming this Gaussian distribution for all the amplitudes, the same will be true. So, I am picking up only two certain amplitude, this one and this one. For that, the distribution is almost equal. So, the probability of the noise acquiring this positive amplitude and this negative amplitude is equal. Therefore, if I just pick two amplitudes +1, -1 arbitrary values, their probabilities are going to be almost equal. And then if we multiply these samples together, the probability of getting 1 and -1 at individual point is also going to be equal. So, if I multiply these individual noise samples at these locations, I am going to get +1 or -1 with equal probability, and then if I sum all these together, the value Vnt times Vn2t integrated over this entire period will again vanish. So, this is how we can demonstrate combining this amplitude distribution and time domain distribution. We can demonstrate that any two uncorrelated noise sources, their overall correlation product will be 0 integrated over a particular time period. And therefore, in order to add the effect of two independent uncorrelated noise sources, we need to look at their mean square values. Same holds true with respect to spectral density. So, if we have spectral density of two noise sources available, one of them having a certain shape, another one having a certain shape, we need to add their spectral densities to look at the overall effect. So, these are the two concepts we need to take keep in mind in order to analyze the circuits. Any question before we proceed towards MOSFET and resistors, look at their noise model and then go for the circuit analysis. Okay. Now, the two major noise sources that we have in the circuits is going to be the resistor noise. So, if you are having a resistor of value R, its equivalent noise source can be modeled as 4 kT/R, means this is your Vn, the mean square noise spectral density of the resistor. That means, for a particular, this is basically representing a white noise because it does not have any frequency dependence. So, it will basically give you a flat spectrum value 4 kT/R, and here I am plotting Vn square per hertz. So, if you want to get the equivalent noise voltage contributed by the resistor in a certain frequency domain, I just need to multiply this with that bandwidth, with this you can call this bandwidth. So, 4 kTr multiplied by this bandwidth, say call it F2 and this is your F1. So, F2 minus F1 times 4 kTr root under will give me the overall root mean square value or RMS value of the noise voltage contributed by this R. So, suppose I am having this R and after that you have put a ideal band pass filter which is having a pass band from F1 to F2, and then you are trying to analyze its effect on a ideal resistor 1 ohm. So, this is a noisy resistor and this is an ideal resistor 1 ohm. I want to see what is the noise voltage delivered by this resistor over here onto the component here. So, for that I need to look at this overall noise produced by this resistor, look at the component between this F1 and F2 bandwidth which is passed by this filter, and then look at the overall noise voltage in terms of the root mean square value. So, we have to go back to the noise spectral density. From there we look at the bandwidth in which the noise is passed. So, if it is a good filter and an ideal filter, it will block the noise components out of the band and it will pass only the noise within the band, and then that gives me the mean square noise voltage over here integrated over this band F1 minus F2 root under that. And then once again here, of course, if you have to look at the exact value, you have to take the voltage division between this 1 and R. So, the division factor will also come into picture. So, here just you are trying to show is that apart from the noise contributed by the component, the other factor that controls the total noise signal at a particular point is the bandwidth through which you are allowing that noise to pass. Now, if you look at the other major noise component that comes into our circuit is because of the MOSFET's noise. So, for the MOSFETs we have two major kinds of noise sources. One is your 1 upon F noise, which is modeled as a voltage source in series with the gate, and another is the channel noise, which is modeled in parallel with the channel. And here the channel current noise is having a similar concept as the resistor noise. So, if you have a resistor, just like you can represent the resistor noise in terms of a noise voltage, you can also convert it into its Thevenin equivalent noise current. So, basically the resistor noise can also be represented by its Thevenin equivalent noise current, which is going to be 4 kT upon R. You will divide this 4 kT upon R square. Remember, this is the Vn square. So, this divided by R square will give you the equivalent noise current that you can connect in parallel with the resistor, and that becomes 4 kT upon R, or 4 kT times G, where G is the conductance of this R. Likewise, for the MOSFET also you have this channel which is conducting the current, and it has some equivalent small signal resistance across which the current is flowing. So, that is going to ultimately control the channel conductance and hence the noise. So, for the MOSFET noise, we have an overall noise channel current represented as 4 kT gamma, which is a constant factor, times Gm, where Gm is the transconductance of this MOSFET, and the gamma is a constant term. It can be within 1. The normally used number is 2 by 3, but it can depend upon the process chosen. So, it can vary a lot from process to process, and it needs to be specified. So, if I assume 2 by 3, then you get an overall expression 8 by 3 kT Gm as the channel current noise of the MOSFET. And remember, the noise current we represented by double arrows because it is not having any defined polarity. It is we are going to deal with the noise current mean square value, and hence the polarity is not of a significant importance. We just denote it by a double arrow to show that the polarity is not of any consequence. Likewise, the voltage source is represented by this star, so that its polarity does not matter in the representation. Now, if we talk about the 1 upon F noise on the gate, that depends upon the W, L. Apart from that, you have the COX and the frequency of the noise, which is F, and then you have the constant term k, which is coming, and it is also dependent upon the process parameter. So, here we have the 1 upon f noise coming at the gate terminal because of the device physics, and it depends upon the area of the device W L, the overall capacitance, and it is having inverse frequency dependence. So, if I look at the noise spectral density, we have the 1 upon f characteristics. That means, if you are looking at the frequency response of the noise signal produced by this 1 upon f noise, it is going to increase at higher frequency. So, we can briefly discuss what is the mechanism of this 1 upon f noise. So, that basically originates from the surface states and the interaction of carriers flowing in the channel with the surface states of the MOSFET. So, you have this channel in a N MOSFET, which is being denoted by this dark region, where you have a lot of electrons shooting from the drain to source, and the interface between the oxide and the channel is imperfect. It has dangling bonds where some of these electrons can get trapped. So, basically there is a continuous trapping, the trapping of electrons going on this interface. Moreover, you are having a gate voltage which may be varying, you are applying some signal, because of which the electric field from the gate to the channel is also varying. As a result, the trapping, retrapping process, which is also going to depend upon this electric field, is also going to vary. So, when the electric field over here increases, you are attracting more electrons, and therefore, the rate of trapping of these electrons will go on increasing. So, whenever at these interfaces you are having trapping sites, for example, where you are able to capture some of the fast moving electrons, when the gate voltage over here goes up, the capturing rate increases, whereas the gate voltage goes down, again it can go down. As a result, you can see this phenomena as a effective reaction between the defect states that you have at the interface and the entities which are getting captured, that is the electrons. So, there are two entities, that is the defect states which are capturing the electrons and the freely moving electrons in the channel, and there are reaction constants. The reaction constant, as we can see, it will depend upon the applied conditions also. If the signal is on the gate is increasing, electric field in this direction increasing, you will end up attracting more electrons at these defect sites, and they will getting trapped more strongly, and on the other side, when the signal goes down, it will be detrapped, and as a result, you have a continuous change of fixed amount of charges that are stored at this interface. So, you are having some spurious charges which are coming at the interface of the oxide and the channel, which are getting changed as per the signal applied, or which are fluctuating over time randomly, and that leads to the 1 upon f noise characteristics that we are observing over here. Now, what are these dependencies that we have, W, L, COX? So, let us look at the COX, which is basically giving us the integration of the electric field produced by this charge across this oxide. So, we know that in order to obtain the threshold voltage, if you go back to the device physics and look at the origin of the threshold voltage, that basically is coming from two components, that is the oxide, the voltage drop across the oxide VOX, and the voltage drop across the silicon VSI. So, when we apply a gate potential on the silicon VG, we have overall voltage drop across the oxide and some voltage drop across the silicon, and here if we look at the voltage drop across the oxide, it depends upon the total charge produced in the silicon. So, for example, when you have a certain gate voltage, you have a depletion region created in the silicon, p type silicon, and you have some inversion charge created over here close to the channel, and as a result, this total depletion charge in the p type silicon and the inversion layer charge combined together supposed to balance the total positive charge that you put on the gate. So, in the silicon, when you are applying the positive potential at the gate for the NMOS, we know that the p type substrate of the NMOS, it will have a lot of holes, the holes will get pushed down, as a result you will produce a depletion region. So, I am drawing the vertical view over here. This is the vertical view looking down into the MOSFET in the vertical direction. This is the vertical view. So, this is if I call this the x direction, this is the y direction, this is the y direction that I have drawn. So, in the y direction, when you are applying a certain gate voltage, it is producing electric field across the y direction, and this P substrate that you have for the NMOS, it is having a lot of holes, and that will be pushing these holes away from the interface and exposing these negative charges. And we know that beyond a certain threshold voltage Vt, you get a lot of negative charges exposed present in the channel region, and you have an inversion taking place, and you have freely moving electrons coming over here. That is the case when you have the channel inverted. So these two charges together, the inversion charge and the electron charge, basically combine together, manage or balance this total positive charge that you have dumped on the gate. And as a result, when you are trying to increase or decrease the gate voltage, the total charge on the gate is increasing or decreasing. That is what we do, right. So while understanding the capacitance of the circuits, also we have discussed that how do the parasitic capacitances arise. So ultimately, it is because of the charge balancing between the gate and the substrate. We are putting more charges on the gate. To balance that, you need more negative charges in the silicon. Likewise, here also, when you are having more positive charges getting accumulated on the gate because of increasing gate voltage, you will have, or you will attract more negative charges over here to balance the electric field produced. Now, if because of this signal you are also having some additional or spurious charge which are random in nature, which are coming at the interface of the oxide and the silicon, which are not under your control, these are random in nature. Because of that, you will have an effective imbalance or change in the channel charge. So basically, now if you are having total trap charge, some net trap charge over here, combination of this trap charge along with the mobile charge plus the fixed charge will be balancing the positive charge over here. And since this trap charge is kind of random in nature, it is randomly fluctuating over time, the total charge over here, the mobile charge required to balance this additional positive charge will also fluctuate over time. That basically means that the effective threshold voltage that you need to turn on the channel, that is also varying over time, because the total charge required over here to balance this deterministic positive charge that you have put on the gate, that is varying over time. So that means the overall threshold voltage that you have for the MOSFET, that is fluctuating over time as you have more and more negative charges coming over here. And in order to look at the COX dependence, we can say that if your negative charges are close to the interface, whatever random charges you have trapped at the interface, they are lying close to the interface, we have an effective electric field produced by these charges, which are going to be balanced by the positive charges over here. And as a result, we have the Gauss law telling us is rho upon epsilon. And if I look at in this region, you do not have any fixed charges. This is the oxide region, you do not have any fixed charges, and therefore in this region, whatever charges you are having, that integrated over this entire distance gives us the overall delta V that is required. And therefore if I just look at the capacitive behavior, the additional charges coming over here, C times the total delta V that is produced across the oxide, that should be equal to the delta Q. So basically COX times the delta Vt, that should be equal to the delta Q that you are producing over time, which is random, which is varying randomly over time because of this noise characteristics. And as a result, the noise voltage, which can be modeled as a minute noise in the threshold voltage, that is dependent on 1 upon COX. So that is how this 1 upon COX terms comes into picture. So the bottom line is, because of this random interaction of the electrons flowing in the channel with the oxide interface, you have continuous trapping of these electrons at the surface. And if I look at the effective voltage drop produced across the oxide, delta V. So this is the random change in delta V that is happening because of the random trapping of electrons. So that is proportional to COX. The COX times the delta V is proportional to the randomly varying charge, and therefore this delta V that is happening across the oxide, it is inversely proportional to COX, and we can model this this random change in VOX as an effective noise term. This is the effective noise voltage which is appearing as a noise component in your threshold voltage. So as a result, you are having this 1 upon COX dependency. So this is the origin of the 1 upon F noise, and then we have other terms coming over here, the 1 upon f term, W and L terms. Why 1 upon f term? Because this damping detrapping process is in general a slow process, and if your signal over the gate is changing much more slowly, the trapping detrapping process will be able to follow that signal more closely. As a result, the frequency component of the noise is more and more towards higher frequencies, lower frequencies. As you go towards lower frequency, the frequency content of the 1 upon f noise increases. Effectively, it also means that if you are integrating this random exchange of these charges, and because of that you are integrating the delta V produced by this random transfer of charges over a long time, it will end up having overall larger magnitude. So, that basically means that at lower frequencies you are having a higher overall contribution because of this trapping detrapping process of the electrons. So, that brings in the 1 upon f factor, and then we have the last two term, which is the W and L, this which gives the total area of the MOSFET. So, that basically comes from the spatial averaging of the trapping detrapping process over the entire MOSFET. So, if you are having the source and drain region, and this is the top view of the MOSFET, you are having the channel over here, and this is the gate region. So, inside this entire gate region, this is the source and drain. So, inside below this entire gate region, you have this trapping detrapping process going on all throughout. So, you have this is the channel length and this is the W. So, I have drawn the top view, looking from the top, this is the view of the MOSFET, and if I look at the spatial averaging. So, this just like you have a time domain averaging that we talked about, right. So, here we talked about the time domain averaging of the noise signal. Likewise, you have this trapping detrapping process going on all throughout this area, and if I go for larger and larger area, this overall summation of this trapping detrapping process will average out, and it will lead to cancellation of this large number of trapping detrapping process which are equal in probability, and as a result you will get lower and lower overall noise signal. So, therefore, the effective noise signal coming because of this interfacial effects that reduces with the increasing area because of this averaging effect, the spatial averaging effect. So, this basically counts for the spatial averaging effect. The COX counts for the integration of this electric field produced across the oxide, and that leading to the delta V change, and then finally, the F corresponds to the following of this trapping process with an low frequency signal, and also integration over a longer period leading to a larger overall noise. So, that is the origin of this 1 upon f noise contribution coming at the gate of the MOSFET, and this basically completes our the noise model that we are going to use for MOSFET. So, I have just given you a qualitative argument explaining these two noise components in the MOSFET, one of them arising from the channel current, which is basically analogous with the noise current of a resistor, and second one because of the 1 upon f noise, which has something to do with the interface effects in the channel of the MOSFET. So, we will be using these two for our circuit analysis, and start our circuit analysis.